Hi guys. I'm not present today, so you're gonna have a little assignment to get started, and it's just some practice with limiting reagents, which is a topic we covered yesterday. So if you were here yesterday, you're in good shape and you can kind of get going. If you weren't, get yesterday's note. It's not a super long one. You can find it on OneNote. The video's there. But I'm just gonna very quickly recap here and then take up the one little kind of homework question I gave you yesterday. And then we can send you off on your way. I'm going to get a periodic table here because we'll need that. And let's get to it. So yesterday we talked about the idea of limiting reagents. And the idea with limiting reagents is just that when we make something from a recipe, say like a sandwich, if I have 2 slices of bread and 3 strips of bacon and 1 piece of lettuce and 1 slice of tomato in every BLT sandwich, when I go to make sandwiches and I have a random number of each of these things, 8 slices of bread, 9 strips of bacon, 12 pieces of lettuce, and 2,498 slices of tomato, I want to know how many sandwiches I can make. Well, I can look at each ingredient and I can see, well, 8 slices of bread would make 4 sandwiches, whereas 9 strips of bacon could only make 3. 12 pieces of lettuce could make 12 sandwiches, and 2,498 slices of tomato could make 2,498 sandwiches. When push comes to shove, it's that 3 that limits me. When I've made my 3rd sandwich, I'm out of bacon. And at that point, I can't make any more BLT sandwiches. So we say that when you look at each ingredient and see how many products you could make from them, the lowest number you get from that list is the actual number of sandwiches you could make. And we say that that's the real number of sandwiches you could make, and that ingredient, the bacon, is what runs out. Then we looked at a comparable example, only this time chemistry. And we said if 4.2 grams of magnesium reacts with 15.2 grams of iron 3 oxide, how much iron could we get? Well, what we just said was, well, okay, let's look what happens if we use all 4.2 grams of magnesium, which we did, and we came up with the fact that 4.2 grams of magnesium, knowing that there's 24 grams of magnesium in every mole, and that in this reaction, we get 2 moles of iron for every 3 moles of magnesium that we use, and that each mole of iron weighs 55 grams, we end up getting 6.4 grams of iron using all of the magnesium. On the other hand, using all of the iron oxide, knowing that iron oxide weighs 159.69 grams, and that you get 2 moles of iron for every mole of iron oxide you use, and knowing that every mole of iron weighs 55.85 grams, we could get 10.6 grams of iron. And so we said, knowing that, we could get 10.6 grams of iron if we used all the iron oxide, but we could only get 6.4 grams of iron if we used all the magnesium. 6.4 is the number we're actually going to get. And the reason we're actually going to get 6.4 grams is because the magnesium runs out. Just like we only get 3 sandwiches because the bacon runs out. So I'm going to try one more of these examples together, and then I'll send you off on your way. So in the second example, I just want to make sure I'm still streaming here. Yeah. In the second example, we said that we had hydrogen gas and oxygen gas in a balloon, and we're going to have them react with one another. And in so doing, we'll produce water. So the first thing, of course, we need is and this is where Hannah yells at me and tells me we need a balanced chemical equation, and Hannah's completely correct. So we know that hydrogen is H, and before I get a chance to move on and be funny, Wyatt's going to yell at me that that's diatomic. And that's going to react with, oh, that's right, Evan, oxygen, O2, also diatomic. And we said it's going to produce water. So that is our balanced chemical equation. If I was there with you, I'd say that, and then you would all scream and shout and say, no, it's not balanced. So take 30 seconds without me and see if you can balance that. What we should notice, of course, is that we only have one oxygen here, despite having two there. So I need to put 2 in front. But that means that now I have 4 hydrogens. And so I need to put a 2 in front there. And I'm sure that Hannah told me that. So thank you, Hannah. Hi, and there we go. Now, we could get going from here, but I always find it helpful to look at molecular weights. Now, we know that this is 2 hydrogens, and each hydrogen weighs 1.01 grams per mole. We could do 1.0079, but I'm just going to do 1.01. And so that means this weighs 2.02 grams for every mole. So a mole of hydrogen gas weighs 2.02 grams. What about oxygen gas? Take a minute and do that. Yeah, well, oxygen is just 2 oxygen atoms, each of which weighs 16.00 grams per mole. And so you put those together, you get 32.00 grams per mole. And finally, water. Take a minute and do that as well. Well, that's those 2 hydrogens at 1.01 grams per mole, and an oxygen at 16.00 grams per mole. So that means every water molecule should weigh 18.02 grams per mole. All right. So that's, as we said before, just setting the table. And now we're going to look and see what we actually have. And what we actually have is that we have 3.7 grams of hydrogen gas, and we have 31.6 grams of oxygen gas. And what we want to know is how many grams of water can be made. So using 3.7 grams of hydrogen. And we can just write that down. We can say we have 3.7 grams of hydrogen gas. And as always, we multiply by a fraction. And what we want to know is how much water can we make? How many grams of water is that? And so we're going to take grams of hydrogen and react it with grams of oxygen to produce grams of water. So in this case, we're going to say 3.7 grams of hydrogen, and we're going to say I don't want grams of hydrogen. Instead, I want to talk always about moles of hydrogen. And where would we get that number? Oh, that is entirely correct. Mantha Kamakai, we look at the periodic table, and the periodic table told us, as we looked up here, that 1 mole of hydrogen gas weighs 2.02 grams. What units cancel? Well, grams of hydrogen would cancel. If I were to stop calculating now, 3.7 times 1 divided by 2.2, I would know how many moles of hydrogen gas we have. But that's not the question. The question is how many grams of water. So I don't want moles of hydrogen, so where is it going to go? That's right, it goes on the bottom. And I'd like to just put grams of water up here. The problem is, can we go from moles of one thing to grams of something else? And we'll say, no, absolutely not. So we can only go from moles of one thing to moles of something else. And where do we get that information? Well, we get that information from the balanced chemical equation, right? And the balanced chemical equation tells us that we produce 2 moles of water for every 2 moles of hydrogen gas that react. What units cancel? Well, moles of hydrogen cancel. If we calculated now, 3.7 times 1 divided by 2.02 times 2 divided by 2, we'd know how many moles of water we've produced. But finally, we don't want moles of water. We want grams of water. And we look here and we see that every mole of water weighs 18.02. And if I were here, I'd do the thing where I write it in the wrong place and I'd make you all yell at me, but I'm going to spare you that. And we'll just do that. And moles of water would cancel. And now, when we do this math, we're going to know how many grams. And really quickly, 3.7. This should be like 1.85 when we work that out. Oh gosh, 1.85 times 10 would be 18, and then almost doubling that. We're going to be in the range of like 33, 34 here, I think. So let's take a look at that. We'd say, okay, 3.7 times 1 divided by 2.02 times 2 divided by 2 times 18.02 divided by 1. We do all that math, and we get 33.0069. All right, and if we just quickly count sig figs, that's 2 sig figs. This is a counting number, so that's infinite. That's 3 sig figs. That's 2 sig, that's an infinite number of sig figs. It's a number 2, but it's a counting number. That's a counting number. This has 4 sig figs, and that's a counting number. It's infinite. So if we look, we've got 2 sig figs to work with, which means the 3 is significant, the 3 is significant, and the question is this 33 or 34? And because it's 33.0, it really is 33. So the answer is 33 grams of water. In other words, if I use all of the hydrogen gas, I could make 33 grams of water. Now that's just like my sandwich thing, where we said, okay, if I used all 8 slices of bread, I could make 4 sandwiches. But here I had to also remember, well, what if I use all 9 strips of my bacon? Oh, I can only make 3 sandwiches with all 9 strips of bacon. So we still have to answer the question, not just based on using all the hydrogen gas, but also if we use all of the oxygen gas. So we're going to have to do all that work a second time. Though this is great because once you get in the habit of this, you discover it's really not so bad. So let's take a look. We have 31.6 grams of oxygen gas. And just like above, we're going to say that we don't want to talk about grams of oxygen gas. Chemistry is done in, that's right, Victoria, moles. And Braden, how many grams of oxygen are in a mole of oxygen? Well, you looked above and you said that every 1 mole has a mass of 32.00. You get that information from the periodic table. Grams of O2 will cancel. If we stopped calculating now, we would see that 31.6 times 1 divided by 32 is going to be about 1 mole. That's about how much oxygen gas we're working with. But again, the question doesn't ask about how many moles of oxygen gas. It wants to know how many moles of water get produced. And we get that information from the periodic table. We know that not from the periodic table. Oh, no, we do not. My goodness, I bet that White Roost is yelling at me as we speak. We get this information from the Ballott's chemical equation. And there's no number in front of O2, which means we have one of those in this reaction. And we're looking at how much water gets produced, and we already said that there's 2 moles of water in this reaction. So moles of oxygen will cancel, leaving us with moles of water. If I stopped calculating now, I'd know how many moles of water get produced. But we don't want moles of water, we want grams of water. And just like above, we said that there's 18.02 grams of water in every 1 mole. Moles of water will cancel with each other. And when we do this math, we should get that. And this should be about, what should this be? This should be about 36 grams, because that is really close to 2 moles there. And each mole of water weighs 18. This should be like 35.8 or so. Let's find out. 31.6 times 1 divided by 32.00 times 2 divided by 1 times 18.02 divide by 1, and we will get 35.6, so I failed. And if we count sig figs here, we'll note that we have 3 sig figs. That's a counting number, so that's infinite. That's 4 sig figs. That's a counting number, so it's infinite. That's a counting number, so it's infinite. These infinity symbols are getting progressively worse, but that's okay. I have faith that you can see them. That's 4 sig figs, and that is a counting number, so it's infinite. And so we have 3 sig figs to work with in this one. So that means the 3 is significant, the 5 is significant, and this 5 either stays a 5 or it will round to 6, and 58 is a lot closer to 60 than it is to 50. So we would say that this is 35.6 grams of oxygen. And now the final question is, which one of these is the answer? If we use all the hydrogen, we can make 33 grams. On the other hand, if we use all of the oxygen, we can make 35.6 grams. And this is just like our sandwich situation, where if we have enough bread to make 4 sandwiches, but we only have enough bacon to make 3 sandwiches, well, we said that's the right answer. So here, if we have enough oxygen to make 36 grams of water, but we only have enough hydrogen to make 33 grams of water, well, then the answer is 33 grams. So therefore, 33 grams of water will be made. Because hydrogen runs out. And that's how we approach a question like that. Now, that is sophisticated. There's a lot going on. It takes some practice. And if you were away yesterday, that may feel like a lot to cover. Don't stress about it. Do your best with it. Get yesterday's note copied down. Get some help from someone who was there. Get some help from Caitlin. Get some help from Tatiana. And certainly I'll be back tomorrow. The assignment isn't due till next week. But it's good practice. It puts everything in this unit all together into, as tricky as I can make one of these questions. We're going to have a lab today. Obviously, since I'm not there, we can't do that. We'll run it tomorrow. If you weren't there yesterday, talk to each other and make sure you know what you're doing. Talk to Tatiana or talk to Caitlin. I want to make sure when we do this lab tomorrow, everyone's ready to hit the ground and just go. All right, see you then.